Hey everybody, welcome back. This is Mr. Lowry here, and we are talking about similar triangles today. Now, some of this information, well, a lot of this information, you can find in your textbook, but I want to kind of talk through some of this, maybe reference where you can find it as well, and kind of talk to you about how we put this together in class. So, there's actually two sections in your textbook that we kind of combined today. The first one is 6.2, which is on similar polygons. And so you'll see that actually the first definition of our lesson today was about similar polygons. Now the reason why I combine these lessons is because triangles are polygons. Poly means many, and so a polygon is a many-sided geometric figure. So all triangles are polygons. All squares, rectangles, parallelograms, those are all polygons as well. Five-sided shapes called pentagons and six-sided shapes, hexagons, those are all polygons. So all the stuff that it talks about in 6.2 about similar polygons applies to similar triangles as well. So in your textbook, like I said, 6.2 is similar polygons, and there's actually a good definition here. This is actually the definition that we took. The example that we used is slightly different because my example was an example of a triangle, and I'll show you that in just a second. But we're going to talk about how we take a similarity statement and break it down into information and what it means to be similar. But you can find some information about that kind of stuff on 289. So that was kind of the important stuff from section 6.2. Okay, and then the next section is 6.3. which is specifically talking about similar triangles. So in similar triangles, there's ideas about proving triangles similar and how you do that and all kinds of stuff. So we're going to talk about a little bit from both sections, and then we'll go through some examples. The other thing that's a little bit different here is that the examples that I wanted to do with you and that I did in class are hard to draw because we're talking about proportionality. So when you look at two triangles and you want them to be proportional, it's really hard to draw them in a way that's proportional. So what I did is I gave everybody in class this handout. It kind of looks like a homework assignment, but the handout goes with the notes. They kind of go together. So we kind of go some definitions and some key ideas, and then we do some practice problems, and then we do some more from the notes, and then we do some more practice problems. So you'll see in my notes I have kind of like blanks where I say, okay, go to example 1 and go to example 2 and go to example 3 and 4. So that's kind of where we're starting. So let me walk you through this a little bit. Okay, the first thing that you should know is what the definition of similar polygons are. Now again, this applies to triangles because triangles are polygons. But that definition is actually in your textbook in section 6.2 on page 289, like I said. But this is it right here. Two polygons are similar if and only if their corresponding angles and are congruent, and the measures of their corresponding sides are proportional. Now this is an important word, that's why I underlined it, because remember, proportional means equal ratios. I also have this little thing that polygon is a many-sided geometric figure, so triangles, parallelograms, pentagons, right, those are all polygons. So like I said, the example in your book, they do a quadrilateral. I'm just going to do a triangle here, since we're going to be talking about triangles today as well. So if I took this little triangle right here, and I gave it side measurements, 8, 5, and 10, and I enlarged it by 2 times, basically what would happen, this triangle would blow up. I'd get a bigger triangle. We call that a dilation. And these triangles would be mathematically similar. Okay, so we know the word similar in English context just means like they have similarities or they have characteristics that are the same. In this case, similarity means something specific. What it means is your angles are still the same. Corresponding angles are the same. So like A and D are the same, B and E are the same, C and F are the same. But notice my sides got twice as big. But I can say that my sides are proportional because their ratios are the same. The ratio of this side to this side, 20 to 10, is the same as the ratio of this side to this side, 10 to 5. Both of those simplify to 2 over 1, which is the same as the ratio as this side to this side, 16 to 8, simplifies to 2 over 1 or 2 to 1. So that's what similar triangles are. It's kind of like, they're almost like congruent triangles, except they're different sizes. Okay, they have the same angles, but one of them's like bigger than the other by a specific factor. So what we would say is that these two triangles are similar. This symbol right here is the symbol for similar. It kind of looks like a congruent symbol without the equal sign part. And this is what we call a similarity statement, a statement that's saying that two triangles are similar. Now, one of the things we talked about in class here that it doesn't really, it talks about this in your book, but it doesn't do the same kind of compare and contrast, is I wanted to take a look at congruent statements versus similarity statements, because we actually already know a lot about congruent statements. Remember from the last chapter, we did triangle congruence and stuff. This is a statement saying two triangles are congruent. And remember that when we know two triangles are congruent, we know all 6 parts of one triangle are congruent to all 6 parts of another triangle. And so I have 3 pairs of angles and 3 pairs of sides that are congruent. And I can do that without even picture, because remember that the position of the letters tells me which points correspond to which points. Right? So point A corresponds to point D, point B corresponds to point E, point C corresponds to point F, which means that angle A corresponds to angle D, and angle B corresponds to angle E, and angle C corresponds to angle F. And since A, B are in position 1 and 2, that corresponds to the segment DE, which are also in positions 1 and 2. And BC corresponds to position EF, because they're in position 2 and 3 and 2 and 3. And then AC corresponds to DF, because they're in position 1 and 3. So we talked about this before. This part right here isn't actually new, but we take a congruent statement and we analyze it, we break it down, we use this CPC-DC to give us all these pieces of information. We kind of unpack that piece of information to give us more information, more detailed information. And we use that information in proofs and other kind of things. Okay, now a similarity statement. Oh, shoot. Glad I caught that. This should be a similarity statement, right? Not a congruent statement. We can unpack a similarity statement in a similar way, but the results are a little bit different. Okay, now here, notice we got congruent, 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 all congruents. Okay, this one's a little different because we start with similarity, but similarity means different things for angles and sides than it does for triangles. Okay, so going back to the definition of similar polygons, two polygons are similar if and only if their corresponding angles are congruent and the measures of their corresponding sides are proportional. So, for example, like A is congruent to D, B is congruent to E, C is congruent to F. That's true. So down here, what I know, if I have these two triangles similar, I can again line up the points A, D, B, E, C, and F, and I can write some information about the angles. So I have 3 pairs of congruent angles. Now, just real quick, we don't ever say that two angles are similar. Oftentimes people will be like, oh, well, congruent triangles means congruent angles, so similar triangles should mean similar angles. And that is not the case. Only polygons can be similar. Angles aren't similar. They're either congruent or they're not congruent. Okay? The same is true for segments. Segments cannot be similar. Segments are either congruent or they're not. Now, we can have proportional sides, and we're going to talk about that next. So the first part, again, of the definition of similar polygons is that they have congruent angles. The next thing says their corresponding sides are proportional. So over here, we said, look, AB corresponds to DE, so AB is congruent to DE. Over here, AB still corresponds to DE, but similar doesn't mean that we have similar segments, it means we have proportional segments. So what I do is I take segment AB and I put it in a ratio with DE. Now that by itself doesn't mean anything at all. AB to DE is meaningless. We want to say that the sides of these things are proportional, and so we need another side pair. So we go to, let's say, AC, right? AC is corresponds to DF, and so I put those guys in a ratio. And also BC corresponds to EF, so I put those guys in a ratio. Okay, so ratio equal to ratio equal to ratio, that's what proportional means. So when you have a similarity statement, what you know about the segments, the sides of the triangle, is their measures are proportional. Okay? Now again, we don't say sides are similar. We never say that. Only polygons can be similar. We say sides are proportional. We say angles are congruent. So I wanted to practice taking a similarity statement like that and breaking it down into pieces, and then we can use those pieces to set up and solve equations. So if you look at the next key concept here in my notes, it says use definition of similar triangles, right? Similar triangles to solve for side measurements. And it says example 1 and 2. So like I said, it's very difficult to draw proportional triangles, proportional sides. So we're going to go to this. So example 1 and 2, I know these look like homework assignments, but this is actually part of your notes. Okay, one of the things I really emphasized in class that I want you to understand as well is that you get a lot of information from this statement. So what I recommend is before you do anything else, before you even look at the picture, don't even look at the picture, just unpack this statement. Okay, well what do I mean by unpack? What I mean is do this. Take this single similarity statement and break it down into the things that you know just based on the position of the letters and the definition of similar. Okay? So I'm going to completely ignore this picture, right? And you should too for a second. Notice that T corresponds to T, and S corresponds to L, and R corresponds to K. We know that because they're in the same position. Okay? That means that angle T is congruent to angle T, and angle S is congruent to angle L because they're in the same position, right? And angle R is congruent to angle K, because remember that similar polygons, in this case triangles, have congruent angles. Their corresponding angles are congruent. Okay? The other thing I can do is I can set up the proportions for the sides. So remember TS here, again, I'm not looking at the picture, don't look at the picture right now, we'll look at it later. TS corresponds to TL. So instead of saying TS is congruent to TL, I'm going to put TS over TL, and I'm going to put them in a ratio. Now that statement all by itself doesn't mean anything. This doesn't mean that TS and TL are proportional to each other. It doesn't mean that TS and TL are congruent to each other. It doesn't mean that TS and TL are similar to each other. It's just a comparison of those two sides. Now, to make a proportion, we actually have to have an equal sign and then another ratio. So I'm going to look at another pair of sides. Let's say S and R. Okay, S and R correspond to L and K. Okay, so I put those in a ratio. And now I'm just going left to right, basically. All right, now let's take a look at the other set of sides that I haven't talked about, T to R, right? So T and R, or segment TR, corresponds to segment TK. So those are my proportions. Now it's kind of weird because like that's obviously a proportion and that's obviously a proportion, but like it gets weird when you have like two equal signs and three sides. But essentially what this means is any two of these will form a proportion. So those two guys, you can set them equal to each other, and these two guys you can set equal to each other, and these two guys you can set equal to each other. So really you only need, to solve a proportion here, you're only going to need two sides. So let's see what information we have. Now remember, all of this came from this statement only. Nothing came from the picture yet. Another thing I wanted to point out is I didn't put like lines on top of these because we're actually talking about the measurements and not the segment itself. We're talking about the ratios of the measurements. So remember, TS is going to be some number and TL is going to be some number and so on. All right, so now let's go back to the picture and start kind of adding and taking information. So angle T is congruent to T. That means these two guys are congruent to each other. Okay, S is congruent to L, so this corner matches up with this corner. And R is congruent to K, so that means this angle here is congruent to this angle. These are the corresponding vertices. All right, that's cool. We also have some information given here in the figure because like TS, for example, we have a number for. So I'm just going to replace that below. So that's 70. And TL we have a number for, right? That's 42. SR I don't have any information about, and neither I don't have any information about LK either, so let's get rid of that, right? And let's talk about TR. So TR I have this guy, 17x minus 4. And TK is, wait, I think I messed up. Sorry, let me go back. TL was 30, excuse me. So TL goes there, TL is 30. TK, excuse me, is the one that's 42. All right, so I don't really even need the middle ratio, but I can say that, you know, if these are all equal to each other, then these two are equal to each other. So I set up the proportion using these two ratios. All right, now once we have a proportion, we know how to solve those. There's lots of different ways. We can try finding a scale factor. We can try finding a common ratio or a common multiple. We can cross multiply, right? In this case, what I'm going to do is I'm going to simplify one of the ratios here. Now we had a conversation in class where we talked about if ratios are the same as fractions, and the answer to that question was yes and no. A ratio, although it's not part to whole, it's still a rational number, and you can still use properties to simplify. So since there's a factor of 10 on top and bottom, we can still cancel those out. That's just going to make my job here a little easier. So if you see one of these ratios that can be simplified like pretty easily, I would go for it before you start solving, because it's just going to make your life easier. All right, so from here, we are going to cross multiply. So 7 times 42, that actually comes out to be 294, is equal to 3 times this expression. And since we're multiplying a binomial, we're going to put that binomial in parentheses to make sure that we, you know, don't only multiply the 17x. Okay, now from here, we have some options too. We can distribute the 3. That's perfectly legal and something you might want to do. We can also just divide by 3 and get it out of there. That works too. 294 divided by 3 actually equals 98. Okay, now it's just a matter of getting x by itself. Instructions, which we probably should have read to begin with, say solve for x. So that's our goal here. So I'm going to add 4 on both sides. That gives us 102 equals 17x. Divide both sides by 17. And we're going to get 6 is equal to x. Or x is equal to 6. All right, so that is how it's done. Now, again, I strongly recommend that if you have a similarity statement, you use that similarity statement first before you do anything else. The pictures are going to be misleading. It's hard sometimes to know how these match up. Like, does 9 go with 36, or does 9 go with this guy, or does 12 go with that guy? Right? It's hard to match them up. Also, sometimes people will go like, oh, 9 over 36 equals 8x plus 8 over 12. So notice I went top to bottom, and then I went bottom to top, and that's going to mess you up too. You can avoid all of that by just using your similarity statement and just looking at it from left to right. So reading it left to right, I know that JK corresponds to WV, so I put them in a ratio. I know that KL corresponds to VU, so I put them in a ratio. I know that JL corresponds to WU, so I put them in a ratio. Okay, now proportional means that all of those ratios should be the same. So I have, this is kind of my guideline. Now, I'm not going to have all these pieces of information, but that doesn't matter because I really only need 2 ratios to solve a proportion. So JK, do I have it? Looks like it's right there. So I'm going to replace that with 8x plus 8. WV looks like this guy. Okay. KL is 36. And VU is 9. And then this stuff I don't really care about. I actually don't have that information anyway, but I don't need it. I already got a proportion that I can solve. Again, this guy is going to reduce. Now you could actually simplify this fraction, but it would require you to factor out a 4 from both of those and then cancel out with the 4 down there, which you could do. That's going to give you basically 2x plus 2 over 3. But sometimes that's confusing for students, and if we don't have to do it here, maybe we should just cross multiply. We'll still get the same answer. So 12 times 4 is going to give us 48. And when you cross multiply, it actually doesn't matter what order you go in. So you could go, this times this equals this times this, or vice versa. 8x plus 8 times 1 is just going to be 8x plus 8. That's pretty easy. So subtract 8 from both sides. 40 equals 8x. Divide both sides by 8. Looks like 5 is going to equal x. All right. Now the next section here of this assignment is kind of the opposite. Here we know triangles are similar, and then we use the proportionality idea to solve for sides. So similar tells us proportional, proportional means equal ratios, right, and so on. The last 6 problems on this assignment are actually going the other way. They're saying, do you know they're similar, or can you tell that they're similar? So in this case, we're not given a similarity statement because we don't know the triangles are similar. We're going to show that they are. We're actually given half a similarity statement, and we have to decide, first of all, if we can finish it, and if we can, then what is it going to be? So we're going to go to the next phase of our notes, and then we'll come back and we'll talk about those problems. All right. So again, I wanted to do a little bit of a compare and contrast with proving triangles congruent and proving triangles similar, because there's some similar ideas here. Okay, now we already know how to show triangles are congruent. So this is ways to show triangles are congruent, I'm just using symbols there. This is stuff we've been using for a while. CP/CTC means if you have all 6 pieces of one triangle congruent to all 6 pieces of another triangle, that's all 3 sides and all 3 angles congruent to all 3 sides and all 3 angles, then you know the triangles are congruent. That was the definition of congruent triangles. From there we talked about shortcuts. Is there less information? Can we have less than 6 pieces of information and still show that triangles are congruent? And the answer was yes, if it's the right pieces of information. So side, 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 congruence postulate, I believe, said that if 3 sides of one triangle are congruent to 3 sides of another triangle, then you can conclude the triangles are congruent. We also had SAS, ASA, and AAS, which were all shortcuts for showing that triangles are congruent. It turns out that there's also shortcuts for showing that triangles are similar. Okay, so we actually have side, side, side similarity. I'm abbreviating that with 4 S's. So side, 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 and then the 4th S is similarity. We got side, angle, side similarity. I'm abbreviating that SAS with 2 S's. And then we have angle, angle similarity. Okay, now what we have to keep a note of here is that these theorems here are a little bit different because we're not trying to show that sides are congruent. Like in this case, S stands for congruent sides, and A stands for congruent angles. In this case, the S stands for proportional sides. And so if we're going to use side, angle, side, or side, 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 we need equal ratios to show sides are proportional. So it's all going to come back to that ratio idea again. So this is kind of how they map out. There is an SSS for similarity. There is an SAS for similarity. These two guys, when we have these 2 angles here, we also know by the third angle theorem that we get the third angle for free. So all we need is 2 angles of a triangle congruent to 2 angles of another triangle. If we have that, then we actually know that all 3 angles of one triangle are congruent to all 3 angles of another triangle, and that's enough information to say the triangles are similar. Essentially what you have in that case, we go back to our first example here, is you have 2 triangles, they have the same angles, it's just one's like a bigger version of the other. So angle, angle similarity is kind of like angle, angle, angle similarity, but remember, you get that third angle for free by the third angles theorem. So I just wanted to point out to you where these are in the book, because this is where they come from. So now we're in section 6.3. And at the very bottom of page 298, you have the angle-angle similarity postulate. If 2 angles of one triangle are congruent to 2 angles of another triangle, then the triangles are similar. Okay? then we have these two guys, side, side, side similarity. Now, your book abbreviates that SSS, but that's kind of confusing because we already have an SSS for congruence. So I'm abbreviating that SSSS, 4 S's, and the fourth S is standing for similarity. Same thing here, they have a side angle side, but I'm using SASS. Okay, so these are actually both going to go in your notes. Actually, all three of those are going to go in your notes, and we're going to use those to help us prove that triangles are similar. Okay, so let's go through them one by one and then practice. So the next section here is the side, side, side similarity. This is actually a theorem. Okay, it says if the measures of the corresponding sides of two triangles are proportional, then the triangles are similar. So that's all three sides in ratio to all three other sides, and the ratios are all equal. So I have like a little note saying go to example 3 and 4. I've left space there. If you want to write them in your notes, you can. You can also just kind of, if you want, print this out or whatever. But in class, like I said, the triangles are hard to draw in a way that shows that they're proportional. The sides are proportional, and so it's a lot easier to just hand this out. Okay, so both of these problems are going to be SSSS type problems. Okay, so in both cases, notice I have 3 sides and 3 sides, 3 sides and 3 sides. So a lot of times students will look at this and be like, oh yeah, okay, yeah, side, side, side. I have 3 side measurements and 3 side measurements, so these must be similar. But remember, it's a little bit harder than that because you have to show that the ratios are equal. So this is how you do that. Without a similarity statement, it's kind of hard to match up which side goes with which. So what you do is you look at the lengths. In the top triangle, I have a short, 17 is the shortest, I have the longest is 25, and I have the medium one, or the middle one, is 24. So when I set up the ratios, I'm going to match short to short, medium to medium, and long to long. Okay, notice the triangles are not in the same position. It's like they got reflected, basically. So be careful about how you match them up. It's a sure bet that you're matching up the right stuff if you use the how the sides are related to each other. So I'm going to go short to short. So 17 is the shortest part of the top triangle. I'm matching it with the shortest part of the bottom triangle. If these are similar triangles, then the ratios of the sides should be the same, the ratios of the corresponding sides. So middle to middle will be 24 to 12. And then long to long will be 25 to 13. Okay, now this ratio right here, 24 over 12, actually simplifies to 2, or 2 over 1. And I know that's not equal to this. And it's also not equal to this guy. And these guys are not equal to each other. So the ratio of the corresponding sides are not proportional, or not, yeah, the sides aren't proportional. The ratio of the corresponding sides are not equal. And so although this looks like it could be side, side, side similarity, when we check, we find out that these are not similar at all. Okay, so now we got the next guy, triangle EFG. Now we're going to do the same thing. So we're going to start by matching short to short, medium to medium, long to long, and set up the ratios that way. So 5 to 35, or 5 over 35, 9 to 63, and then 11 to 77. Okay, are those all equal? In fact, they are. They actually are all equal to 1/7. So the ratios of the corresponding sides are equal, which means the corresponding sides are proportional, which means we can say that these are congruent, not congruent, similar by the side-side-side similarity theorem. So the 3 parts of this. First, state if the triangles in each pair are similar. They're similar. If so, state how you know. Similar by side-side-side similarity, and then complete the similarity statement. So we got to figure out the matching sides. This can be a little bit tricky, but again, match short to short, medium to medium, and long to long. So this side is the short side, has to correspond with this side. So it's pretty easy to see that E matches with E and F matches with S. So E matches with E, F matches with S, which means that T has to match with G. And if you pick another side, like the medium, for example, it's pretty easy to see, oh yeah, F goes with S and T goes with G. So we completed the triangle similarity statement. We said it was similar, we said it was by SSS similarity, and we finished the statement. Okay, so that's one method to show that triangles are similar. Not the only method, it's just one of them. Okay, there's two more. The other one is the side-side-side similarity theorem. Okay. And this is also in your book. Again, this was on page 299. So the very top of 299 is SSS similarity and SAS similarity. So this is a little wordy. We'll explain what it means. If the measures of two sides of a triangle are proportional to the measures of two corresponding sides of another triangle, and the included angles are congruent, then the triangles are similar. Remember that the included angle we're talking about is an angle formed by the two sides in question. So this is an included angle for these two sides. So let's take a look at some example problems to talk about how we can use SAS. And again, we're going to have to check the ratios. So what we want is angles that are congruent and sides that are proportional. So we're going to go to examples 5 and 6 here. All right, so if we look at number 5, you'll notice that we have that triangle and that triangle. And they're actually both sharing angle B. And since angle B is congruent to itself, we know that these guys have an angle in common. So the little triangle and the bigger triangle have a congruent angle. Okay, now notice that that angle is the included angle for BS and BT. It's also the included angle for BC and BD. So if we can show that BS over BC is equal to BT over BD, then we know that these sides are proportional, which means we could say these triangles are similar by side, angle, side. So just like with congruence, we want side, angle, side in that order, but in the sides that we're talking about, we don't want the sides to be congruent, we want the sides to be proportional, which means we need ratios. The other thing that's kind of weird about this one is the scale is all off. So we actually need to know the length of this side, which we don't have. We know the full side, B to C, is 80, and we know that this section from S to C is 70, which means the leftovers must be 10. 80 minus 70 is 10. 10 plus 70 is 80. But if you think about that, this little section is 70 and this huge section is 10. Doesn't really make sense to scale. Now your textbook and word problems or questions will do that to you from time to time to test that you're not trying to assume too much. A lot of times it will purposely make figures that aren't drawn to scale to see if you're making extra assumptions, like from your own visual cues, versus just using the information provided. On the other side, we have something similar. From B to D, that full length is 96. That's what this is measuring. But this section from T to D is 84. So the leftovers is 96 minus 84, and that's going to give us 12. So I already know angle B is congruent to angle B, right? The trick now is to find out if we have the sides in the sides proportional. So the ratio of BS to BC is going to be 10 to 80. And that supposedly should be equal to the ratio of BT to BD. That's 12 to 96. Okay, it turns out that both of those rational numbers will simplify to 1 over 8, which means that we have a pair of proportional sides and their included angle is congruent. So these triangles actually are similar. So we're going to say similar by side, angle, side, similarity. throwing that extra S on there to distinguish it from our side angle side congruence theorem, postulate, excuse me. And then we got to write the similarity statement. Remember that the similarity statement has to be in a specific, like the order of the letters is important because it tells us which parts of the triangle correspond. So obviously point B corresponds with itself. It looks like S corresponds to C. So on the little triangle, this corner of the little triangle corresponds to this corner of the big triangle. So B corresponds with B, C corresponds to S, and then D, the corner of the big triangle, must correspond to this corner of the smaller triangle. So BST. Okay, so there's multiple parts of that problem. We want to say that it's congruent. We want to say how we know. Sorry, not congruent. We want to say it's similar. We want to say how we know. And then we want to finish the similarity statement. Okay, we got another one. Both 5 and 6 are going to be SASS type problems. We just got to check the ratios. In this case, you might notice that we have vertical angles. So it looks like we might be able to show these two triangles are similar by side, angle, side. Side, angle, side. The tricky part is we can't just assume that these sides are in ratio just because we have their measurements. We actually have to check those ratios, check to see if they're proportional. Okay, again, sometimes it's tricky to see how the sides match up. Like some people might say, well, 70 goes with 42 and 139 goes with 22. But in this case, the triangles aren't like flipped around. They're actually in the same orientation. I know that because if this is the shorter side of these two, it must correspond with the shorter side of these two. Right? So 70 has to go with 22 because those are the two shorter sides on the triangle. 139 has to go with 42 because those are the two longer sides of the triangle. So the ratio I want to set up is something like 70 over 22 should equal 139 over 42. Now this simplifies to 35 over 11 because 2 goes into both of those. This one I'm not quite sure on. I think it might simplify. Let's check it out. Okay, it actually doesn't simplify. So those definitely are not equal to each other. So I wrote that they were equal, but they're actually not. So I can't use side angle side here. I mean, I have a side measurement and an angle congruent to an angle and a side measurement, but because these sides are not proportional to each other, they don't have the same ratio, I can't say that these triangles are similar. So forget about the similarity statement. These are not similar. Okay. Now we actually saved the easiest one for last, which is nice. So the third way that we can show triangles are similar is angle-angle similarity. Now this was actually a postulate. And all we need is 2 angles of one triangle congruent to 2 angles of another triangle. Then we can show the triangles are similar. Now this actually sounds very, very similar to what we called the third angle postulate. The third angle theorem. The third angle theorem says if 2 angles of one triangle are congruent to 2 angles of another triangle, then the third angles have to be congruent as well. So the if part of those two, of this postulate and that theorem are the same. The then part or the conclusion is a little bit different. So all we need are 2 pairs of congruent angles to show triangles are similar. And again, the reason why is because we get the third one for free by the third angle theorem. So let's go back. So 7 and 8 are both angle-angle similarity type problems. One of them's congruent, one of them we can conclude similar and the other one we can't. And let's take a look at why. So one thing that we do get in number 7 is vertical angles. So I'm going to mark these 2 angles congruent because they're vertical angles. And I'm using 4 dashes because I already got 1, 2, and 3. But that being said, this is really my only pair of congruent angles. These aren't congruent because they don't have the same number of markings. These aren't congruent for the same reason, and neither are these. So I only have 1 pair of angles that I know for sure are congruent, The other ones I don't know anything about, and I also don't know anything about the sides. So although it kind of looks like it's tempting to think this is angle because I got some other angles in there, these are actually showing that none of these angles are congruent to each other. So these triangles are not similar. Okay, now this one's cool. I like this one. It uses an idea that we've talked about quite a bit. It's hard to see on camera, but in person, it's a little more obvious that these are arrows here. Now that doesn't mean congruent, so be careful. It just means parallel. However, when we have parallel lines, we always want to look for alternate interior angles. And so this would be, for example, a pair of alternate interior angles that would have to be congruent because these lines are parallel. We also have these alternate interior angles. We have two sets because we have two transversals. And so we can say these triangles are congruent by angle. But just for fun, we also got this vertical angle here, vertical angle pair. So really we have three pairs of congruent angles, which gives us more information than what we need. So we're going to say these triangles are similar by angle. You can pick whichever two you're interested in using. S corresponds to S. That's pretty obvious here. U corresponds to N. Those are the angle, the alternate interior angles. So this U is going to correspond to N, and then M corresponds to T. So T and M will be in the same position there. All right, that is basically it. So on your homework, you're going to have, whoops, that's the wrong one. You're going to have some similar problems. It's actually set up very similar to this. So use this as a guide, as example problems to kind of help you set up and solve proportions in that assignment. Okay, I hope that was helpful for you. Thanks for watching, and we'll see you back in class soon, hopefully.